Hey Pre-Calculus, I've got a new video for you. It's over section 3.6. It's all about inverses of functions. So, before I talk just straight up about how to find inverses, I should probably explain what it means. So, a function is considered to have an inverse if it's 1 to 1, which means every element of the input functions, normally x, corresponds to exactly one element of y. Corresponds to exactly one element of y. And vice versa. So every y goes to only one x. So when we see this, hopefully you guys can see that well enough. If you see these two functions right here, -5 only exists once for all of the x values. So does 14, so does 12, so does 4. For the y values, 4, 8, -1, -3. There's no y value repeats. There's no x value repeats. Which, if that's the case, then you know that it is indeed 1 to 1, which means it has an inverse. Same thing over here. 4, -3, -1, 5, no overlap of the x's. -4, 2, 4, -12, no overlaps with y's. So that can give you utmost confidence that G is 1 to 1, F is 1 to 1, and that they have inverses. From a graphing approach, 1-to-1 functions pass both the vertical and horizontal line tests. So in graphing, 1-to-1 functions pass both the vertical which means that there can only be one y per x value, and horizontal, which means that there can only be one y value per x value. Line tests. Also, from a graphing perspective, inverse functions. So let's say that this is the original function. Its inverse looks like this. They are reflections of one another over the line y equals x. So here's the line y equals x. Basically, the distance that any point on the purple is from the red should be equal distance. And furthermore, you are just going to be flip-flopping the x and y values. So, if you had to go over 4 units, up 2 units to get on red, so over 1, 2, 3, 4, up 1, 2 to get to this point, then its corresponding point on the purple graph should be just the swap of it. 2, 4. All right. Now, I've said a lot about inverses. Let's dig into the actual examples. So number 1. If you're given a data set full of ordered pairs, if somebody were to tell you to find the inverse functions, you are literally just reversing the x and the y values. So -5, 4 becomes 4, -5. 8, 14. -1, 12. And -3, 4. And the same is true for the g's. negative 4, 4, 2, negative 3, 4, negative 1, and then 12, 5. Sorry, I'm thinking if I can give you guys an example on the fly with these inverses that are similar to the function composition, and I'm just not coming up with anything right now. So, it's okay. Actually, no. I got one. Okay, so, remember function composition where we had to, hold on, that's not working out right now. Remember when you guys did f of g of x, but you had to do these ordered pairs? Think if you had to do f of g inverse of 4. Yeah. Yeah, what would that look like? Well, the first thing you do is you'd say, well, I'm going to go to my g inverse function. My x value from that function's 4. It yields a value of negative 1 inside here. And then f of negative 1, you'd go over here. Negative 1 corresponds to 12. So the data point would be 4, 12 that gave you that. So I don't know, I just wanted to connect it. I wanted to connect it to something that you saw earlier. So now some trickier things. What happens when equations show up? We talked about the data set. We talked about the graphing perspective. What happens if you're just straight up given one equation and you're asked to find the inverse? Well, think about it from this perspective. The graph reflects everything over the line y equals x. So it's literally saying reverse, just like a reflection image of yourself, it's everything is reversed of what it should be. You are taking the x-coordinate and the y-coordinate for every data point in the function and swapping it. So what do? We envision each function as a y value, that's our output, and an x value, that's our input. And then all we got to do is swap the x's with the y's. So that y becomes x. These x's become y values. And when we do that, we have created f inverse. This new function is now f inverse of x. It's not written well because the y isn't by itself, but that's what our next task is going to be. All right, so you switch out the x's and the y's, and then get y by itself. So to get y by itself, I'm gonna break up this fraction, cross multiply. 1y equals, take the x times both parts, so it's gonna be 1x minus 2xy. Okay. We're not done yet. We gotta get y by itself. Move all the y values together. So I'm gonna add 2xy to neutralize it here, and then add it over here. It's probably getting tougher to see, so I'm going to write it up here. Well, maybe not yet. 1y plus 2xy is equal to 1x. Now here's the point at which you have to do kind of a tricky move that maybe you guys wouldn't think to do off right at the top of your head. If I want to isolate y, okay, I can't combine these two. Look, I can't add if there's multiplication right here. But what I can do is I can factor out that y value. So I can take that red y, do a reverse distributive property move, and then 1 plus 2x is what's left inside the parentheses. All right, on the right-hand side, you get 1x. And you know what? That's exactly what we need to divide by in order to get that y value by itself. So, y by itself, that's technically f inverse of x, so I'm going to do the replacement. It's not y, it's f inverse of x is equal to this function. X over, and I'm just going to commute 2x plus 1. There's our inverse function. Now, what's the domain of it? Actually, you know what? I'm going to highlight something here with number 2 that should be a super good helper for this idea of how the domain and range of the original connect with the domain and range of the inverse. So, and then I'll take a break after this video because we've been going in all sorts of different directions. So think about the original. When we talk about the domain, we should be thinking that the bottom can't be 0. Bottom can't be 0. Everything else is good, though. So if the bottom can't be 0, it's going to be all real numbers work for x, except x cannot be a half. The range of our original, it's not the bottom, because the bottom gives the vertical asymptote of a rational function like this. It's going to be the horizontal asymptote that's important here. The 1 divided by -2, if you remember your rules of asymptotes last chapter, that basically tells you that, hey, all my y's are okay, except you can't have it equaling 1 over -2. That's where my horizontal asymptote lives, so that can't be a part of my range of values. Now notice, for our inverse function, its domain, or its vertical asymptote, is 1 plus 2x cannot be 0, which would require you to minus 2x from both sides and divide by -2. It's everybody except x can't equal -1/2. And its range, again, we'll talk not vertical asymptotes like what you have on the bottom, but horizontal asymptotes. 1 over +2. So everybody but y can't equal 1 over +2. Basically, the flip-flopping of our x's and y's continue. The domain represents all the x's in your function, which will represent all the y's in your function for the inverse. I'm sorry, you couldn't see that, could you? Darn it. Can you see them both now? So the domain of the original are the x's of the original. The range of the inverse are the y's of the inverse. They match. Everybody but a half, everybody but a half. The y's for the original, everybody but -1/2. The x's of the inverse, everybody but x can't be -1/2. They match. So bottom line, here's the big concept. The domain of the original is the exact same set. So I'll put the word equals, but I don't mean equals as in like 5 equals 3 plus 2. I mean same set. No, I'm going to put equals just so it's simple for us to remember. Equals the range of the inverse. Big concept right here. And then vice versa is true as well. The range of the original equals the domain inverse. big concepts. All right, I feel like we need to take a break. 15 minutes is kind of a long time, and we still have a few examples to go through, so thanks for watching. Part 2's coming up for 3.6.